It is nice when a function is given in the form y is equal to some expression containing x alone. An example, y is x squared is nice because if you give me the value of x, I can evaluate the right hand side and I have immediately the function value y. We can also differentiate this formula and we have the derivative. So this is nice. When the function is given in this way, we say it is given in an explicit way. However, sometimes situation is more complicated. We can always transform this explicit definition of the function into the implicit one. We can say that y minus x squared is 0. And now we have some expression on the left containing both x and y and the condition that this expression should be equal to 0. And this is called implicit way of giving the function. Actually, the adjective implicit refers to the way of defining the function. So we should say function given in an implicit way. But as an abusive notation, we use implicit function and we mean the way. So sometimes we can transform the implicit way into the explicit way. Sometimes it is not so easy if we have, say, x plus y plus sine of x divided by y minus 3 is 0, then no way to write the function in the explicit way. So in general, we can have some expression here, and let's call it capital F of x and y. If we look at the function fxy alone, without equals 0, and we can call it a function of two variables. If the function capital F is continuous and has continuous derivatives, we can imagine the graph of the function being a two-dimensional surface in a three-dimensional space. And then the condition that f is equal to 0 means that we take this graph of the function and we consider the cut of the xy plane. And in a typical case, this cut is actually a zero-level contour line. And the question is whether we can look at a small piece of this contour line as a graph of some function y is the function of x. Sometimes we can, sometimes we cannot. So the definition goes this way. We say the equation fxy is equal to 0 defines in the implicit way a function y is f of x in some neighborhood of a point x0, y0 if first the point must be on this curve. That means the point must satisfy the equation. Here x and y are variables. Here x0, y0 are two numbers, two values. So this is the number, and if it is equal to 0, we say that this point satisfies this equation, or the point lies on this curve, if it is a curve. And we want that there is some neighborhood of x, 0, and some neighborhood of y, 0, such that for each x in this neighborhood, y is f of x is the only solution to this equation. We are considering only some small neighborhood of x and small neighborhood of y. That means we are considering some small rectangle around x0. We don't mind if the curve goes like that. We don't mind if for this x there are more than one values of y satisfying this equation if it is out of our neighborhood of interest. So we look only at the local situation near the point x0, y0. Let us consider a few examples when the implicit function exists, and some examples where it does not. Consider the equation x squared plus y squared minus 1 is 0. If you rewrite this into the form x squared plus y squared is 1, then you recognize that this equation is the equation of the unit circle. Then, if we consider, say, this point, x0 is 0, y0 is 1, then indeed this point satisfies this equation, and there is some neighborhood of this point such that we can look at the small piece of the graph, or the small piece of the contour line, as a graph of y as function of x. These points this is no problem, the existence of these points, because they are out of this small neighborhood. However, if we consider the point x0 is 1 and y0 is 0, then it is not possible to consider a small piece of this curve and to look at this as a graph of a function. Because to the right of x0, no solution, and to the left, we have two solutions. In any neighborhood, small as you wish. So this is not a good point, or this equation does not define an implicit function near this point. Another problem is if the curve, if the contour line consists of two or more lines that cross. At this point, we cannot look at this curve as a graph of as a graph of a function y, a function of x. The sufficient condition for the implicit function to exist looks like this. We want the point to satisfy this equation, and we want the partial derivative of f with respect to y at this point x0, y0 to be different from 0. This is quite natural condition, because if you have some expression containing x and y, and we want this to be equal to 0, so it may be technically difficult or even impossible to write it in the explicit way, but nevertheless, y must be there so that we could at least consider a function like that. Even if we have not the formula to write it down, but y must be there. If there is no y, then y cannot be expressed in terms of x using this equation. Y must be there. But if you say x squared plus y minus y must be there. Y is there. But actually it is not. Y minus y is 0. So y must be there in some important way. Important way means that this depends on y. It changes with y. And this expression, changing with y, means that the derivative must be different from 0. So this is a sufficient condition, along with this one, for the implicit function to exist. Well, so if we know what it is, implicit function, if we know the condition that it exists, we want to find some properties of the implicit function. It would be nice to be able to find the derivative of the implicit function. If we consider the equation fxy, and if we want y being a function of x, look that we have two different functions, not to be confused. We have the function capital F. This is a function of two variables, and this is given in the explicit way. This is the left-hand side of the equation, and we have this. We see this expression for capital F. And then we have the function small f, which is function of just one variable. And usually this is not given in the explicit way. This is only given by the implicit way, and we have not the formula for small f. So bad news is we will never see the formula for small f. But the good news is that even though we don't have the formula, we can find its derivatives. Because if we write this in the form fx is 0, and we want this to be identically equal to 0 for all x in some interval, then we can differentiate this. And if this expression is identically equal to 0 for all x in some interval, then even the derivative will be 0. Well, and this is a composite function, and we know how to differentiate a composite function. Derivative of f with respect to the first argument times derivative of x with respect to x, which is 1, plus the derivative of f with respect to the second argument times the derivative of the inner function, which is f derivative, f prime, small f. And this is equal to 0. If we subtract this derivative, we have a partial derivative of f with respect to y times f prime is minus partial derivative of f with respect to x. And under the condition that this derivative is different from 0, which agrees well with this condition for the function to exist, we can divide, and we have the derivative of small f minus fraction partial derivative of f with respect to x divided by partial derivative of f with respect to y. And this is a very, very useful formula which allows us to evaluate the derivative of a function that we will never see in our life, meaning the function. So you can differentiate a function which you do not have at all. Great.